The roadmap to 6G represents a fundamental leap beyond the data-centric services of today toward a future of connected intelligence. At the heart of this vision is integrated sensing and communication, or ISAC, a foundational pillar merging two worlds into one. Driven by spectrum scarcity and the move to millimeter wave and terahertz bands, ISAC enables unprecedented resource efficiency. By sharing hardware, waveforms, and spectrum, we can maximize both spectral and power efficiency across the entire 6G network. In this 25-minute technical masterclass, we will explore the engineering breakthroughs that are making ISAC a reality. We begin with the fundamentals, the integration hierarchy, ranging from basic coexistence to full dual functionality. Radio communications coexistence, or RCC, involves shared spectrum use where separate hardware and waveforms are coordinated to manage interference. The higher level is dual-function radar communications, or DFRC, which uses the exact same hardware and waveform for both functions. Waveform design is the critical first step. We move from sensing-centric and communication-centric designs to a truly integrated joint DFRC waveform that serves both functions optimally. The transceiver hardware is where the integration comes to life. By sharing the RF front end, including power amplifiers and antenna arrays, we achieve a massive reduction in complexity and power. Intelligent metasurfaces, or RIS, allow us to control the radio environment. By adjusting the phase of meta-elements, we can steer signals around obstacles and create multiple spatial degrees of freedom. In the 6G near-field, the traditional far-field planar wave model fails. We must account for spherical wavefronts, which enable precise beam focusing at specific 3D coordinates. The ultimate convergence is ISCC, integrated sensing, communication, and computation. This closed-loop symbiosis allows nodes to sense raw data, compute for intelligence, and share that knowledge seamlessly. As we bring 6G to the sky, we require a dual-layer heterogeneous network topology. This 3D architecture ensures continuous signal coverage for both ground-level users and uncrewed aerial vehicles. In complex urban environments, targets are often hidden within environmental clutter. Advanced signal processing extracts the clean target echoes from stationary background reflections. To achieve simultaneous transmission and reception, we utilize in-band full duplex. This requires extreme self-interference cancellation, effectively neutralizing the powerful transmit signal to listen for the faint radar echo. Beyond reflection, simultaneous transmitting and reflecting RIS panels, or star RIs, extend signal coverage to a full 360 degrees, serving users on both sides of the surface. ISCC enables a new era of distributed intelligence. Through techniques like federated learning, 6G nodes collaboratively train AI models using local sensory data without compromising privacy. In the smart factory of the future, ISAC allows robotic systems to navigate precisely and coordinate tasks in real time, powered by a seamless blend of sensing and high-speed data sharing. This integration transforms our network management into a unified, intelligent control plane, where sensing, communication, and computation are managed as a single coordinated resource. Radar sensing begins with waveform design. Traditional systems use pulsed signals, but 6G leverages frequency-modulated continuous wave, or FMCW, to achieve high-resolution ranging and velocity detection simultaneously. By applying the fast Fourier transform, we can extract the Doppler frequency shift from these waveforms, allowing us to estimate the precise velocity of moving targets in the environment. Advanced waveforms like orthogonal time-frequency space, or OTFS, are being developed to handle the high mobility and complex delay Doppler characteristics of the 6G channel. Phased array antennas are the workhorses of ISAC, focusing energy into highly directional beams to maximize gain while minimizing interference through side lobe attenuation. We distinguish between passive and active metasurfaces. While passive RIS elements reflect signals, active elements integrate power amplifiers to overcome the quadruple path loss in radar sensing. In the near field, we use specialized codebooks for beam training. These grids of potential focal points allow the base station to search for a user's 3D coordinates with pinpoint accuracy. To save bandwidth, we utilize task-oriented feature extraction. Mobile nodes process raw radar data locally, sending only relevant feature vectors to the edge server for decision-making. Modeling the atmosphere is crucial. Ducting layers can trap signals, extending their range, but also creating long-distance interference that must be managed in the 6G network. Fluid antenna systems represent a paradigm shift. By moving the antenna element along a microscopic track, we can physically find the point of peak signal strength in real time. The journey to 2030 is guided by global standardization efforts. From 3GPP Release 19 through Release 21, the technical specifications for ISAC are being finalized. In-band full duplex is the engine of ISAC. By integrating analog and digital self-interference cancellation, we enable the transceiver to transmit and receive on the exact same frequency block. A key engineering challenge is the power wall. As we increase sampling resolution at high bandwidths, ADC power consumption rises exponentially, necessitating highly efficient data conversion strategies. Semiconductor innovation is at the core. Gallium nitride power amplifiers provide the high thermal conductivity and power density required for the terahertz and millimeter wave operations of 6G. Linear multiport interferometric networks allow for signal extraction without traditional power-hungry mixers, offering a new pathway for high-efficiency signal demodulation. By comparing linear and nonlinear transceiver paths, we see a clear trade-off between power efficiency and harmonic distortion, guiding the design of future 6G front ends. Massive MIMO scaling laws are the mathematical foundation of 6G. As we increase the number of antenna elements, the array gain grows quadratically, enabling the high-precision beams of the future. The virtual receiver matrix architecture allows for dynamic element activation. Individual sensors in the matrix are powered on demand to optimize for specific sensing and communication tasks. At the base station core, we perform real-time joint waveform synthesis, merging separate sensing and communication signals into a single optimized 6G pulse. Radar cross-section modeling is vital for target identification. Heat maps of target reflectivity points help the 6G network recognize drones, vehicles, and other objects with high precision. At the microscopic level, an RIS unit cell consists of a copper meta-element integrated with a semiconductor tuning circuit. This allows for precise dynamic control of the signal's phase and amplitude. The phase control circuitry manages voltage inputs to each meta-element. By shifting these voltages, we can steer signal energy across the environment without the need for active amplifiers. StarRes uses an energy-splitting protocol. A single incident wave is divided between reflection and transmission zones, with power distribution optimized for both sets of users. Operation is governed by mode switching or time splitting. Elements can either function as purely reflective or transmissive, or alternate between states across the communication frame. Group-connected architectures for beyond-diagonal RIS offer a balance between complexity and gain. Meta-elements are clustered into hexagonal groups with interconnected routing paths. We define the near-field boundaries using the Fresnel and Rayleigh distances. As antenna apertures grow in 6G, this region expands, demanding new spherical wave modeling. Unlike far-field beam steering, which covers a wide wedge, near-field beam focusing concentrates energy onto a tiny 3D focal point, enabling high-precision targeting. Spherical wavefronts radiate from large-scale arrays in concentric arcs. These complex dynamics provide richer spatial features for sensing and more degrees of freedom for communication. To minimize latency, we use hierarchical beam training. A broad initial search is narrowed down through multiple refinement stages to find the user's exact coordinates. In the near field, channels are non-stationary. Signal properties and wavefront curvature visibly change as a target moves through the spatial zones of a massive array. Discriminant gain is a vital metric for split AI inference. By separating task-relevant feature vectors from raw data, we can optimize the communication path for maximum classification accuracy. Unsupervised learning allows the ISAC system to adapt to the environment without labeled datasets. Neural networks process the raw signal stream to find the optimal beamforming weights in real time. Deep reinforcement learning agents are used to design UAV trajectories. By utilizing a reward-based feedback loop, the drone learns to navigate for peak signal strength and sensing coverage. Long short-term memory, or LSTM networks, are ideal for channel prediction. They capture the temporal dependencies of the fading channel, allowing for proactive resource allocation. Cloud RAN enables large-scale cooperative ISAC. Multiple base stations are connected to a central cloud processor, allowing for joint signal processing across the entire urban grid. In a multi-static radar network, distributed receivers capture echoes from multiple angles. This fusion architecture provides a comprehensive view of the target, enhancing recognition accuracy. We compare monostatic and bistatic geometries. While monostatic systems are simpler, bistatic configurations offer better interference management by separating the transmitter and receiver. The pulse repetition frequency determines our sensing resolution. A higher PRF improves velocity detection but leaves fewer time slots for data communication, requiring careful optimization. Wave domain processing on metasurfaces offers near-zero latency compared to digital processing. This shift is critical for the ultra-fast decision-making required in the 6G era. Energy efficiency is the final design constraint. The 6G ISAC dashboard allows us to balance the power consumption of sensing, comms, and computation across the entire network. Resource allocation utilizes TDM, FDM, and CDM multiplexing. By coordinating these resources, we can ensure that sensing and communication tasks coexist without mutual interference. Alternating optimization algorithms are used to solve complex resource problems. By iteratively updating variables, the network converges on an optimal balance for all tasks. The goals for 6G are extreme: peak data rates of 1 terabit per second, sub-millisecond latency, and a connection density of 10 million devices per square kilometer. Predictive beamforming anticipates the movement of autonomous vehicles. By projecting the vehicle's path, the base station can pre-align its sensing and communication beams. 6G will support massive IoT density. Thousands of sensors and devices will be connected in a seamless grid, providing ubiquitous intelligence across our cities. Haptic communications will allow for tactile feedback over the network. This enables immersive remote surgery and teleoperation with high precision and near-zero delay. ISAC is the key to creating digital twins. By scanning our physical environment in real time, we can build a perfect virtual replica for simulation and management. Physical layer security is enhanced by ISAC. By utilizing the sensing channel knowledge, we can maximize the secrecy rate and protect our data from unauthorized eavesdropping. Artificial noise injection scrambles the signal for unauthorized users. This technique ensures that only the intended recipient can decode the high-speed data stream. Covert communications hide the very existence of our signals. By camouflaging signal beams below the noise floor, we can ensure secure and private network operations. Holographic radio utilizes extremely large-scale arrays to generate pencil-thin beams. This technology provides the high spatial resolution required for 6G precision sensing and massive connectivity. By moving to continuous aperture metasurfaces, we eliminate the discrete nature of antenna elements. This allows for the generation of complex, seamless wavefronts that can be precisely shaped in real time. Holographic pattern division multiple access, or HDMA, assigns unique spatial patterns to different users. This approach enables the network to serve an unprecedented number of devices simultaneously. Aerial RIS mounted on drones provides a mobile solution for signal blockage. By reflecting signal beams around skyscrapers, we can maintain reliable ISAC links even in the most complex urban corridors. Drones also act as mobile base stations. Equipped with compact ISAC transceivers, they can provide temporary coverage and sensing services for industrial factories and remote locations. The 6G vision integrates space, air, and ground into a unified mesh. This SAGEN architecture connects satellites, high-altitude drones, and terrestrial towers to provide global ISAC services. Low Earth orbit satellites play a critical role in Earth sensing. By integrating communication and radar functions, they provide a 3D view of our planet while maintaining high-speed ground links. The integration of ISAC is foundational for the metaverse. By syncing the physical and digital worlds in real time, 6G enables the creation of highly accurate digital twins for every urban environment. Remote healthcare and robotic surgery are powered by 6G. High-precision sensing and haptic feedback ensure that every delicate movement is transmitted with clinical accuracy and zero delay. As we look toward 2030, integrated sensing and communication is not just a technology, it is the fabric of a new, intelligent world that is constantly sensing, learning, and sharing. Artificial intelligence is redefining channel estimation. Deep neural networks can now process complex pilot signals to extract precise channel state information, even in high-mobility 6G environments. Deep reinforcement learning agents optimize beamforming policies in real time. By navigating a complex action-reward landscape, the network learns to maintain peak connectivity under changing conditions. Bayesian inference provides a robust framework for target sensing. By updating prior environmental knowledge with new radar echoes, we achieve a highly accurate posterior map of our surroundings. Tensor decomposition allows us to break down multidimensional signal data into its core components. This complex processing is vital for separating multiple targets in a crowded urban grid. Privacy is paramount. Secure federated learning ensures that local model updates are encrypted before being shared, allowing nodes to build a global intelligence without exposing sensitive raw data. We utilize discriminant gain to optimize split AI inference. By maximizing the separation between data clusters, we ensure that only the most relevant features are transmitted across the 6G link. In the V2X ecosystem, every vehicle acts as a mobile sensor and communication hub. This creates a hyper-aware network where cars coordinate movement via real-time ISAC data. Collision avoidance systems are powered by real-time sensing. By predicting target trajectories and calculating safe avoidance paths, 6G ensures safe navigation for autonomous platforms. Environmental monitoring is a key ISAC use case. 6G base stations can now scan the atmosphere to monitor rain, pollution, and climate patterns with unprecedented spatial resolution. High-speed railways demand ultra-reliable links. ISAC signal beams track the train's precise position, maintaining high-speed data connectivity even at velocities exceeding 300 km per hour. In advanced manufacturing, coordinated robotics rely on ISAC for sub-centimeter precision. Robotic arms work in sync, sharing both sensing data and task commands across a low-latency 6G mesh. The future 6G base station is a multifunctional powerhouse. Integrated with massive arrays and edge computation pods, it serves as the intelligent brain of our connected world. Bessel beams are a unique class of non-diffracting waves. By engineering these concentric wavefronts, we achieve a central beam that maintains its focus over long distances without spreading. Airy beams possess remarkable self-healing properties. Even if partially blocked by an obstacle, the beam can reconstruct itself, ensuring stable ISAC links in cluttered environments. We utilize energy and time splitting protocols to manage star-rice resources. This allows the network to balance the needs of reflective and transmissive users across each communication frame. Stacked intelligent meta-surfaces perform signal processing in the wave domain. SIMs can execute complex matrix multiplications with near-zero latency, outperforming digital processors. In extremely large-scale arrays, we must account for spatial non-stationarity. As a signal traverses the massive aperture, its properties change, requiring adaptive near-field modeling. Subspace rotation is a powerful optimization technique. By aligning the sensing and communication subspaces, we can minimize the fundamental trade-off between accuracy and data rate. Cooperation across multiple cells is essential. Through Cloud RAN architectures, 6G base stations coordinate their signal beams to provide seamless coverage across the entire urban grid. Angle Doppler spectrum estimation, or ADSE, is used for target detection. By analyzing 2D peak maps, the network can precisely identify the position and velocity of every target. Multi-subcarrier joint detection, or MSJD, enhances our sensitivity. By combining data across multiple carrier lines, we can detect faint target echoes that were previously hidden by noise. Hardware reconfigurability is key. The dual-mode Gilbert cell allows the transceiver to switch between sensing and communication modes in real time, maximizing resource utilization. Holographic radio achieves massive connectivity through pencil-thin beams. These ultra-narrow paths allow the base station to serve thousands of drones and devices with minimal interference. The 6G network will be built from modular nodes. Integrated with computational pods and solar power, these base stations provide sustainable, intelligent infrastructure for our future. In conclusion, the fusion of sensing, communication, and computation is redefining our world. 6G is not just a network. It is the foundation of a new, intelligent digital reality. Urban microcells will be the backbone of 6G. By strategically placing base stations and RIS panels, we can provide a seamless, high-capacity mesh that covers every street and vehicle. Indoor coverage is optimized through intelligent reflections. RIS panels on office walls can steer signal beams into every room, ensuring that 6G connectivity is as robust indoors as it is outside. UAV swarms coordinate their sensing tasks via 6G. By sharing their radar perspectives in real time, the swarm can build a comprehensive 3D map of large-scale environments with extreme accuracy. Satellite backhaul meshes extend 6G to the entire planet. Multiple LEO satellites connect terrestrial hubs to space-based sensors, creating a global unified ISAC infrastructure. The haptic teleoperation loop requires ultra-low latency. 6G ISAC ensures that tactile feedback from a remote robotic arm is delivered to the operator in less than a millisecond. Model pruning and quantization are vital for edge AI. By simplifying neural networks, we can run complex inference tasks on low-power 6G mobile devices without sacrificing accuracy. Distributed ledgers provide a new layer of security. By securing 6G network configurations on a blockchain, we can protect against unauthorized access and ensure the integrity of sensing data. Quantum-secured 6G will be unhackable. By utilizing entangled particles for key distribution, we can ensure that every communication and sensing task is protected by the laws of physics. Terahertz frequencies offer massive bandwidth but face signal absorption peaks. Modeling these attenuation patterns allows engineers to select the best frequencies for 6G ISAC tasks. Autonomous driving is the ultimate 6G test case. With real-time radar sensing and high-speed data tracks, 6G ensures that vehicles navigate safely through complex urban traffic. The Intelligent Control Center provides a global view of the 6G network. Operators can monitor sensing metrics and communication loads across the entire planet from a single holographic interface. In the clinical environment, 6G ISAC enables remote robotic surgery. The high-fidelity sensing and low latency ensure that surgeons can perform delicate procedures from across the world. Smart agriculture relies on ubiquitous sensing. 6G base stations and drones monitor crop health and soil conditions, allowing for automated high-precision farming across vast agricultural lands. Next-generation vehicles will feature transparent HUDs. Real-time radar sensing of surrounding traffic and pedestrians is projected directly onto the windshield, enhancing driver safety and awareness. Digital twin simulation allows us to test new 6G configurations in a virtual world. By analyzing signal wave interactions with digital replicas of machines, we can optimize the network before deployment. Global standardization is the roadmap to 2030. The collaborative efforts of 3GPP and ETSI ensure that 6G ISAC technologies are interoperable across all nations and industries. The manufacturing of 6G hardware requires extreme precision. Automated clean rooms and robotic assembly lines produce the sophisticated CMOS and GAN chips that power the ISAC ecosystem. The future mobile interface will be transparent and data-rich. 6G ISAC provides real-time 3D visualizations and environmental data directly to the user's handheld device. In conclusion, 6G is building a fully connected world. By integrating sensing, communication, and computation, we are creating a global intelligence that will redefine our future. Thank you for joining this technical masterclass. The ISAC revolution is just beginning, and we look forward to the connected, intelligent world of 2030. The optimization of 6G networks requires balancing multiple conflicting objectives. The Pareto optimal front allows us to find the perfect equilibrium between latency, reliability, and spectral efficiency. Dynamic spectrum access allows the network to adapt to real-time traffic demands. Signal blocks shift seamlessly across frequency bands to ensure maximum throughput. and minimum interference. Joint radar communication processing unifies our signal chain. By using a shared generation stage, we can efficiently recover both high-speed data and precise radar echoes. Cooperative perception allows vehicles to see beyond their immediate line of sight. By sharing radar point cloud data, the network creates a comprehensive map of the urban environment. Waveform slicing allocates specific signal segments to different services. This ensures that industrial sensing, mobile data, and critical control tasks all receive the optimal waveform properties. Edge computing is integrated directly into the 6G base station. Modular pods handle intensive computational tasks locally, reducing latency for time-critical autonomous applications. Physical layer security protects our data at the signal level. By utilizing the unique properties of the wireless channel, we can create an unhackable shield for our communications. Interference cancellation across multiple cells is vital. By coordinating signal waves from different towers, we can neutralize interference at the cell boundaries, ensuring stable coverage. Holographic beamforming generates hundreds of thin signal paths. This technology allows the 6G network to track large swarms of drones and IoT devices with extreme precision. Semantic communication focuses on the meaning of data. By transmitting only essential semantic icons, we can massively reduce the required bandwidth while maintaining perfect understanding. Real-world field trials are validating our 6G visions. Prototypes in the field are demonstrating that ISAC can achieve the high-speed and high-precision targets we've set for 2030. Terahertz mesh networks provide dense urban coverage. High-speed beams connect small cells throughout the city, creating an intelligent infrastructure for the smart city of tomorrow. Ultra-low latency decision loops are the brain of the network. By merging sensing and computation, we enable autonomous systems to make life-critical decisions in real time. Ray tracing modeling ensures precise network planning. By simulating every signal reflection in a 3D city grid, we can optimize base station placement for perfect coverage. In summary, we have covered the pillars of 6G, unified DFRC, meta-surface control, near-field precision, and the ultimate convergence into ISCC. Hardware prototypes are proving the viability of holographic ISAC. This 1D model uses a layered waveguide substrate to control 16 individual metamaterial elements via precise bias voltages. Stacked intelligent meta-surfaces offer significant performance gains. By increasing the number of sim layers, we can reduce the angle of arrival estimation error from 3.6 degrees to just 1.4 degrees. In star-RIS architectures, the energy splitting protocol is vital. It allows for the dynamic division of the phase shift matrix between reflection and transmission zones, serving users across the full 360-degree space. Cooperative mobile crowd sensing leverages the power of every device. By connecting thousands of mobile sensors to a central cloud, we create a hyper-aware urban sensing network. Semantic data processing is the future of efficiency. By compressing complex raw data into high-level meaning icons, we can serve more users while using less spectrum. Edge AI optimization is achieved through model quantization. This process compresses massive neural networks into lightweight cores that can run locally on 6G mobile hardware. Interference nulling is a critical beamforming capability. By perfectly zeroing out signal energy in the direction of undesired users, we maximize the reliability of our ISAC links. Quantum-secured links will protect the 6G network. Through entangled particle pairs, we can ensure that every communication and sensing task is secured by the laws of quantum physics. Scaling to extremely large arrays expands the near-field region. The Rayleigh distance grows quadratically with aperture, unlocking new 3D spatial features for the next generation of wireless. The 6G R&D centers of today are building the world of tomorrow. Through sterile clean rooms and advanced antenna labs, the hardware for 2030 is already being forged. Robustness is built into the 6G fabric. Self-healing networks can instantly reroute tasks when a node fails, ensuring that mission-critical ISAC services remain online. Precision haptic feedback loops require absolute synchronicity. 6G ISAC ensures that every nuance of pressure and force is transmitted across the globe with zero perceived delay. HDMA will power ultra-massive connectivity. By assigning unique holographic spatial patterns to every user, the 6G base station can serve thousands of devices simultaneously. Stacked intelligent metasurfaces perform wave domain processing. By executing complex matrix math directly in the electromagnetic field, SIMs achieve near-zero latency for 6G tasks. The global path to 2030 is paved with standardization. Collaborative releases from 3GPP and ETSI are defining the technical milestones for the ISAC revolution. Discriminant gain optimization ensures that our edge intelligence is focused. By sharpening the separation between data clusters, we maximize the accuracy of our distributed AI models. Modular base station infrastructure allows for rapid 6G scaling. Integrated with computational pods and advanced cooling, these nodes provide sustainable intelligence for our smart cities. In conclusion, the intelligent 6G world will be built on the foundation of ISAC, a world where every signal senses, every node thinks, and every device connects. Covert ISAC will protect high-security missions. By camouflaging signals within the digital noise, we can ensure that critical operations remain hidden from unauthorized observers. Thank you for joining this 25-minute technical masterclass on mastering 6G ISAC. The future of wireless intelligence is now in your hands.